Welcome to lecture 7, which is about rotations in 3 dimensions, and specifically we will be looking at angular momentum in 3 dimensions. Now what do I mean by that in 3 dimensions? Well, so far all our rotations have happened in one and the same directions. It was counterclockwise or clockwise. Yes, maybe we looked at it from an angle like this, but if I have a disk here that's spinning in one direction, then it's going to continue spinning, maybe changing the angular velocity, maybe going faster, spinning slower. But at no time have we wondered what happens if I try to change the axis from pointing up to maybe pointing like this, like over here. Right, those two disks, they're spinning with different angular velocities, even if they might be spinning at the same speed, let's call it that, at the same rate, right? Because they're spinning in different directions. Oh, look at this disk over here that I attempted to draw. So here's a disk, and it's spinning not along an axis that points through the center of the disk, but one that kind of points through the side. So you could imagine this axis here, it's coming towards us, it's disappearing in the distance here, kind of into the paper, hard to draw in 3D, and it's spinning around like a sort of plate that's flat like this, and then it comes to be like this, not one that spins around its center point, like its axis. So the different types of rotations that an object can have in all 3 dimensions. Now one part we have to do here is we have to describe those different kinds of rotation. Just how do I mathematically express the difference between those two? But then the more interesting part is going to be to ask what happens if I have, say, a disk like this and it's spinning, and I apply a torque that's in a different direction from the angular velocity that's already there. So if I apply a torque that's not making this disk that's spinning speed up or slow down, but say I'm pushing down on the edge here, so I'm sort of pushing down like this, what's going to happen? Is the disk going to do this and keep spinning around its axis? Is something more interesting going to happen? That is where it gets, I don't want to say really complicated, but you really have to think hard about it. And you have to try to visualize it all in 3D, and I'll do what I can to show that on paper. So here are some examples of situations where you might have seen this kind of effect, where I have something spinning in one direction, but then I'm applying a torque to it in a different direction. It doesn't directly add or take away from the angular velocity that's there, but it sort of tries to change its direction. One is riding a bike around a turn. So I ride in one direction, right, and you can imagine that the wheels are turning with a certain amount of angular momentum. If I'm trying to turn the direction my bike is going, I have to turn the axis of rotation of the wheels. That's going to happen with a torque, but the torque is not there to make the wheels speed up or slow down, but to change their direction. So we're going to see how that works. Spinning top, like a sort of hits top, you spin it and it spins super fast, and if it sort of spins like this, but it might sort of slowly rotate like this. If you've got a top on it that you can just spin on your tape and you try it, you take it and you spin it. I don't have one right here, unfortunately, and it'll not just spin around its own axis very fast, but it also do this sort of slower rotation where you can see its axis of rotation changing. You call it the precession of a top. Very similar principle applies to gyroscopes. Now gyroscopes, it's not something you like see all the time, but they're extremely useful. For example, if you want to maintain a constant direction when you're out in space and you have no sort of points of reference. They're also just very interesting in themselves as examples of angular momentum conservation, and I'll show you some demos in the process. Another super interesting example is you take a tennis racket and you throw it upwards and make it spin. Now actually, analyzing that is going to go somewhat beyond what we can do in this course. And I tried my hardest to see if I could find some way of explaining the physics of throwing a tennis racket upwards and having it spin in certain directions. But I have found no way to include it essentially in like a single lecture here without doing 4 other lectures beforehand that teach you mechanics that is somewhat more advanced than what is expected of you in this course. Of course, it shouldn't stop you from trying to understand it. But what's the mystery here? The mystery is, imagine like a tennis racket, so it might look like this. Very poorly drawn tennis racket. It could be a badminton racket, whatever you like to play, right? So here's a racket. Now, this thing could spin around the axis like this, right? So I have it and I can spin it. It's very easy to do. You can do like in your hand, like this pencil spinning like this. If you throw it up, you can also have it spin. Let me draw it from the side. Here's the tennis racket, very poorly drawn, clearly. Maybe sort of spin like this. That'll work. But what if you try to have it spin so that it, as if it were trying to catch a lot of flies, so sort of spinning with its this side coming towards you. Really hard to show on paper. It turns out that 2 ways of making it spin is easy and stable. If you try to flip it up in the 3rd direction, make it spin around the 3rd axis, you're not going to manage to do it. It's going to try to spin in a different way. So there's something here it's called the intermediate axis theorem. Also sometimes called the tennis racket theorem, for the obvious reason that that's a prime example. That will essentially says there are 2 axes around which this can spin in a stable way, but if you try to spin it on the 3rd axis, the racket will adjust its direction of rotation. So it's to do with the stability of rotation around particular axes. It's super interesting stuff. Now, I suggest you just look this up, go online, maybe on YouTube, you find some kind of examples of this, so you can at least see what I'm talking about. Understanding it is a different story that requires some more advanced mechanics than we've been able to cover so far, or that sadly we have time for in this course. The reason I'm including it here is to show you there's of course a lot more to this topic of rotations in 3D than I'll be able to cover in the rest of this lecture. But we'll definitely look at those 3 examples. Maybe not the top, actually. In this lecture, we're going to reserve this for our class session. But the other 2 for sure. So let's get started by trying to actually describe rotations in 3 dimensions. So how do I describe the direction of angular velocity? Like, how do I make angular velocity a vector? And so here is how we do this. So omega is now a vector. I'll put an arrow on top. The magnitude of it is the rate of rotation. That's the thing we've dealt with so far, how many radians per second. And the direction is the axis of rotation. So the direction of this vector omega is defined as pointing in the axis of rotation. So in this case here, the vector omega would be represented by this. Of course, there is the question of, is omega this way or is omega the other way, right? The axis still has 2 directions. It's like a 50-50. So there we're going to apply what's called the right-hand rule, and it's the right-hand rule that looks like this. You take your thumb, and your thumb points in the direction of the vector, then your fingers sort of curl around. The way they curl around, that is the direction of rotation. So it can be more easily seen if you take like a pencil, and I put my thumb in the direction of the pencil, and then my fingers, they curl around like this. So if I look towards the point, the fingers go around counterclockwise. So imagine you look towards this point from up here, you'd see a counterclockwise rotation. Whereas if I were to look from down here, I'd see the vector pointing away from me, then I'd see the rotation being in the clockwise direction. Kind of hard to do. There is a picture in the textbook that is page 370. You can see this. Now, if you have studied magnetism, magnetic fields, then you're sort of familiar with the right-hand rule like this, namely when it came to figuring out what is the direction of the magnetic field around a current-carrying wire. It's exactly analogous, except now the thumb is the direction of the vector, and the fingers are the direction of they point in the direction of the rotation. So if this is rotating this way in front and this way in the back, then my fingers to point in the direction of rotation, I'd have to have my thumb point down. So in this case, omega would point like this. Of course, the magnitude of omega gives me the length of the vector, tells me how fast the thing is spinning. So omega is perpendicular to the plane within which the rotation occurs. It's another way of saying it is in the direction of the axis of the rotation. It can be hard to draw sometimes, so if I take an example, maybe like this, and I look at it from above, there's a disk that's spinning like this. When I look straight down onto it, and the axis is coming straight towards me, then using my right hand, the thumb points in the direction of the vector. If it's up, yes, that makes sense. That corresponds to the spinning in the counterclockwise direction. So here I'd have to draw the vector coming towards me, which of course I can't really easily do on paper. Whereas if it were spinning the other way, so write this down, omega towards us, we might say out of the paper. Whereas if it were spinning in the opposite direction, like this, then to make this happen with my fingers, I'd have to point my thumb down, right? You can't, there's no way I can have my thumb point up and my fingers point in the rotation in the same direction as this. I have to hold my hand like this to make this happen. So in this case, omega away from us, or into the paper. So this is how we can think of angular velocity as having a direction. It's not just clockwise or counterclockwise, right? It's actually in three-dimensional space. Now, of course, I could have this object here rotate in a different direction. So I could have said, this is my object, and it looks like this from the side, from my viewpoint, but it's rotating in a different direction, in which case I'd have to change the angle. So if I go back to what I had before, right, if this was spinning this way, then the angular momentum would point backwards into the page, whereas here it would point down, and here it would point this way. So this is kind of example similar to what I've just drawn. In this case here, the axis is not through the center, that's okay. If you want to represent the orientation of an object in 3D space, never mind which way it's spinning, we'd normally use something called Euler angles, but I'm not going to go into that in this lecture. Again, because we probably need a few lectures of time to just sort of make sense of those and see how to use them effectively. All right. So now we understand how angular velocity is a vector. Now, what about angular momentum? But angular momentum is also a vector. And that is fairly easy once you understand angular velocity. So it's a vector, L, right? Still the same letter, but with an arrow on top, meaning vector. Or if it's printed, you sometimes just see it in bold print. Oops. That is, of course, just equal to the moment of inertia times omega. With the moment of inertia, of course, defined around the axis of rotation, right? The moment of inertia is always defined relative to an axis of rotation. For example, if you have a stick, remember the moment of inertia of a stick, of a rod, is different if you rotate it about the center than if you rotate it, say, about one of its endpoints. Right, so you've got to pick the right moment of inertia. Alright, so this is angular momentum. Essentially it points the same direction as angular velocity. It's just multiplied by the moment of inertia, which is a just a number, well, with units, but it's not a vector. But you have to pick the correct one for our purposes. Okay. So now the question is, well, what about torque? Let's draw this out. Let's see what happens to torque. Okay. So imagine this spinning disk, right, and it has a angular velocity that points up, which means right-hand rule means it's of spinning this way, right? If I draw this, it means it's spinning like this. Now let's imagine I apply a torque to this, and I apply the torque in the direction F as shown. If I try to draw this from above, I have a top view. It helps with more than one view sometimes. Right, then it would look like this. This would be R, and then F would just be like this. So here I try to draw it in 3D. This is just in 2D. So what would this do? This force, right, would clearly accelerate the disk. It would apply an angular acceleration, make it spin faster. Because it's a torque that's in the same direction as the angular velocity. So seen from above, right, it's spinning counterclockwise, and then the torque, something pushing at this point in this direction, would make it speed up. So maybe the disk is spinning, you put your finger down and you use friction between your finger and the disk to make it spin faster. Hopefully you agree with that. So somehow we have to make the math work out that a force applied to a point here in that direction from the axis creates a torque that adds to the angular velocity vector that's pointing up. So it's a bit of like a mathematical riddle, if you like. So here is how we're going to define torque in 3D. So torque, right, becomes a vector. It's still tau, but now it's a vector. And I'm going to define torque as R, so the vector now that connects the midpoint to the point where the force is applied. And I'm going to take the cross product with F. And we're going to talk about the cross product a bit in a second. Cross product also appears, for example, in magnetism. And if you've studied magnetism in the past, then you've met it there. So another way I could write this, of course, is that the torque is still dl by dt. And I could write this as R cross F. If the moment of inertia is constant, I might have I alpha, where alpha has a direction now, and so on. So I've got to show to you how this works out, right? But the key to remember about the cross product is the cross product. It takes two vectors, turns it into another vector. So this vector is equal to this combination of those two vectors combined in a particular way to make another vector. R cross F. There's two vector inputs. It spits out this function called the cross product, spits out a third vector, and that vector is going to perpendicular to those two. That's what we see here. This one is horizontal, this one is horizontal, like in the plane of the disk, and then it's going to create a torque that points straight up. So those together create a torque that points like this. Force applied in that direction at a point that is whose displacement from the center is in the r direction creates a torque in the upwards direction. Upwards direction, again, right hand rule. It's pushing the rotation in that direction. Like it adds to the omega, right? Torque is I could write it as torque is still equal to d omega dt times I, the moment of inertia, if I is constant. Right, so the torque, if the torque is in the same direction as the angular acceleration, angular velocity, it'll just add to the angular velocity, like make it bigger. The opposite direction, it'll make it smaller. That's the situation we've been dealing with so far, except we didn't describe it in those terms because things were generally just defined around just one axis. We looked at it from above, the spinning, and that was that. So let's take a moment, let's take a little bit of an aside to review how the cross product works. So here's our quick review. You have two vectors, I'm going to call them A and B, and you combine them via this cross product operation. It gives you a third vector C. Right, so this is our definitions of vectors. I'm going to show you how to calculate C from the components of A and B in just a second. But first, I'm going to show you how to calculate it essentially by looking at the angles and the directions. So A cross B is C, right? C has then the following properties. C is at right angles to A and at right angles to B. So that means we have to be in 3D, right? I can't draw two vectors on a page and find a third vector that is perpendicular to both, assuming A and B aren't in the same direction in the first place. So, like if this is A and this is B, then C would point straight up. So it's right angles to both of them. Always in 3D. The cross product, also called the vector product sometimes, it only makes sense in 3 dimensions. In 2 dimensions, you just like C doesn't exist, like it doesn't make any sense. Right? You need to have 3 components to your vectors. Now the question is, well, there are 2 vectors here, right? The question is, what direction is C? Is it up or is it down? The 2 vectors that are perpendicular to A and B, up or down. And to some extent that is an arbitrary definition, like math would still work if we define it the other way. But the way we talk about the cross product, what we mean by it is C pointing up, and the way to determine this is by another right-hand rule. So we had this right-hand rule for the rotation. Now we're going to have a right-hand rule like this, where we actually hold our right hand like this. I'm going to say A, B, and then C is my middle finger. And you can tell that even if A and B are not perpendicular to each other, like they're more like this, there's still only one direction in which my middle finger can point. Right? If A is this way, B is that way, that means my middle finger would be pointing down. Of course, you have to make sure you use the right hand and not the left hand. Okay, so another way you can do this, another way to do the same the same right-hand rule with your right hand is you say A, you hold your hand like this, you say A, B, and then A cross B gives you C, and C sort of points straight out of your palm. It's another way to do it. Sometimes it's easier to do this without like breaking your wrist as you're trying to make your fingers point in the correct direction. And don't use your left hand. I've done it before. Check out page 318 in the textbook. Right, that'll show you pictures where you can see those directions. One consequence of this is if I take the cross products of B cross A, it's the other way around. It'll change the direction. So A, B, C, but if I want to flip A and B, then A would point this way, B points this way, then C would have to be pointing down. So we say this is it's not commutative. Commutative means A cross B is B cross A. That's not true, but it's anti-commutative, meaning A cross B is equal to minus B cross A. It's the opposite direction. All right. Now let's figure out how I can calculate C algebraically if I have the components of A and B. So sometimes you'll be able to do it this way, especially when A and B are sort of in a plane, like the XY plane, then C is going to be in the Z direction. But what if A and B are in some arbitrary direction? So here's how you calculate it. So calculate the cross product algebraically. How do I do this? So I'll write my vectors A as AX, X component, Y component, Z component. You write your B as X component, Y component, Z component. Now you could do the IJK notation as well. You can do any notation you want, but I find this the easiest one to use. So, X component of A, Y component of A, Z component of A. Then A cross B is equal to AX, AY, AZ cross product BX, BY, BZ. I'm going to do an example with actual numbers in just a second. Now, this gives you one new vector with 3 components, 1, 2, 3. Now, to compute each component, you look at the components in the other 2 directions. So to compute X, I'm going to look at Y and Z. To compute Y, I'm going to look at Z and X. And to compute the Z component, I'm going to look at X and Y. And the way to do this is to do it crosswise. So for the X component of C, right, the combined vector, the result, I'm going to essentially take this times this minus this times this. A, Y, B, Z minus A, Z, B, Y. Now, for the Y component of this, here, I want to kind of go AZBX minus AXBZ. One trick to not get confused which way around it is that you repeat the components again down here. I'm just going to write the same values again. That's just a notational trick to make your life easier. And then to get the Y component, I'm just going to go one row down, and I'm going to go this way minus this way. AZBX minus AXBZ, or BZ, right, depending on if you're British English or American English. Then, to get the Z component, or the Z component here, I'm going to go from the Z row, I'm going to go one down, I'm going to start here, I'm going to go this minus this. So it's AXBY minus AYBX. And this vector, right, this is going to be one value once you've plugged in all the numbers. This vector has the properties that I described here. Now, I'm not going to prove this right here. You can do it in a math course. Maybe you've done it in a math course. Hopefully, you've seen that in some math course. In the American system, it's very strange that the cross product is usually taught in some calculus course, like Calc 2 or Calc 3, depending like what kind of system you're in, which is really strange because it has nothing to do with calculus. Like there's no derivatives, no integrals here. It's just a way to combine vectors, so it should really be part of algebra, but it's not how, for some mysterious reason, it works in the American system. If I were in charge, you'd be learning this in some algebra course you take before you move to any kind of calculus course. All right. Beside the point, I'm not in charge. This is how you do it. Let's do an actual number. So I'm going to start with two very simple, let me get a new page actually. Let me start with two very simple vectors that I can actually draw on paper. So example 1. I'm going to have A be equal to 5. Oops, wait a minute, it's not a 5, it's 0. 5, 0, 0. So it means its x component is 5, the other components are 0. It's a vector that points along the x-axis and is 5 units long. For B, I'm going to pick 3, 3, 0. So if I draw those, this is my z direction, this is x, this is y. Good thing in 3D, of course. Then maybe I should make A green. Then A would look like this, 5 units long. Let's make B blue. B, it has both an x and a y component, and it's the same. It's 3, so it might look something like this, 3 and 3. It's point in this direction here. So you can tell right away from the right-hand rule that C would be pointing straight up, because it's, I have to turn this, so I have to use my hands. X, Y, my middle finger points up. So C is gonna point straight upwards in the Z direction. No X or Y components. Let's check algebraically that that's true. So C is A cross B, so 5, 0, 0 cross 3, 3, 0. So to work this out, I'm going to repeat the first two down below, 5, 0 and 3, 3. And then I'm going to start at the x point. I'm going to move 1 down. 0 times 0 minus 0 times 3. It's going to be easy. Right? 0 times 0 minus 0 times 3. Okay, now I'm going to find the y component. So I'm going to start here, move 1 down. 0 times 3 minus 5 times 0. Told you this would be easy. So far we haven't got very much. And the last one, I'm going to start at the z, and I'm going to move 1 down, back to the x essentially. 5 times 3 minus 0 times 3. Now most of those are 0. As I said, I pick a very simple example for our first one. We get 0, 0, and then 15. So really I should make this a lot longer. It's 15 units long. Now let's try this the other method, right? So here I know this angle here is 45 degrees. How do I know this? Because this one here is 3 and 3, means it's exactly halfway between the axes. Right? It splits those two angles in two because it's the same x, the same y. So I know this is 45 degrees. Let's work it out the other way. So C, right, is in the in the Z direction only, like we drew, but 15 units long. So that matches the direction. What about the magnitude? Our claim is it's equal to this. And then it's the sine of the angle between them. In this case it's 45, theta AB. So A, the magnitude of A is 5. It's 5 long, right? The only component. Easy to calculate the magnitude. What's the magnitude of B, the vector B? Well, it's 3 and 3, so I'm going to use the Pythagorean theorem. It's going to be the square root of 3 squared plus 3 squared, which is difficult. Square root of 18, what's that? Let's wait a moment. And then I'm going to multiply this by the sine of 45. Sine of 45 degrees is 1 over root 2 times 1 over root 2. Now you can do the math here. You combine the square root. You're going to get 5 times the square root of 18 over 2. Which of course nothing but the square root of 9, which brings me back to 3. So this is indeed 15, like what we found before. So in this case, the two methods, doing it algebraically and doing it via this method here, the right-hand rule and calculating the magnitude like this, it does match. So it's reassuring. Right. Let's do another example of the algebraic way of calculating this. So example 2, this one's going to be a little bit harder. We want to say A is equal to 1, 0, and 3, and B is going to be equal to 2, 2, and 2. Now I'm not going to attempt to draw those because this one kind of goes in all three directions. So it goes along the x-axis, the y-axis, and also the z-axis. If I attempted to draw this, it just wouldn't really work in 2D. You wouldn't be able to see what's going on. It would probably be more confusing than helpful. But we can still just work it out algebraically. What the cross product is, A cross B is equal to 1, 0, 3. I'm going to repeat the first two entries, the x and the y, crossed with 2, 2, 2. I'm going to repeat the first two, that's still 2's. So x value, I'm going to start 1 down, 0 times 2 minus 3 times 2. Then for the y value, I'm going to start with y, I'm going to move 1 down, 3 times 2 minus 1 times 2. And then for the z value, let's start at z, I'm going to move 1 down, 1 times 2 minus 0 times 2. Like this, right? 1 times 2 minus 0 times 2. You can work this out. This is minus 6, so don't forget the signs. Signs matter. Signs determine direction. And then 6 minus 2 is 4. And then this is just 2. That's a bit harder to check, but if you know how to, you can again double check that the magnitude of this matches what you would have calculated if you've done this. Of course, how do you find the angle between those two vectors in the first place? If you know about the dot product, maybe you can use that. Alright, so for the most part in this class, we're not going to spend a lot of time doing those kinds of calculations. What's more important is that we understand those properties here. That's going to be more relevant for the examples we are going to look at. Alright, so now we've covered all the preliminaries. We understand how to define angular velocity and angular acceleration and angular momentum and so torque in 3D. Now we are ready to look at some examples of what happens when the torque is not in the same direction as the existing angular momentum. To get started on that, I'm going to show you a little demo.